Physics 30s, how's it going? So today we are going to talk about refraction within lenses, such as the ones in your glasses and stuff. And we're going to be talking very specifically about ideal thin lenses. We're not going to delve into the reasoning behind why we're going to talk about just thin lenses and not like thick, bulgy lenses. The main reason is that we want to just deal with having the light within the lens itself for the least amount of time. So having it too much time within the lens adds a little bit more error, and it creates unfocused images that you can deal with. You can actually recorrect by changing the way the shape of the lens is, but we're only going to deal with very simple thin lenses. And the two types of lenses that we're going to talk about are converging lenses and diverging lenses. And sometimes they call them differently. They sometimes call them convex and concave lenses. But we're going to reserve those two terms for mirrors, and we're going to use converging and diverging for lenses, so we know what we're talking about in each case. I'll try not to mix them up too much. Now, a nice converging lens looks like this. It looks like a little cat eye, kind of oval shape, and it's called converging because if you have a bunch of lens or rays that come straight across, all parallel to that principal axis that we had before, they will converge at one point. We call that principal focus point. Okay. And on the other type of lens that we have divergent lenses. You can see that's the other way around, so it's more like an hourglass shape. And the reason they call these divergent lenses is that parallel lines will come out. They will diverge as they refract out the other side. And if you were to trace them back, though, you'd have a virtual principal focus point here. And then the focal length is that. There's no center here for these kind of diagrams. So you're not going to worry about 2Fs, so that's the center point over here. We're just worried about the focal point in all these cases. Okay. Now, we can draw the lens diagrams. Now, you don't necessarily have to. I'm never going to ask you to draw these lens diagrams out. But rather than drawing them out, just make this video just a little bit shorter. Let's just look at this applet that we have here. So here's a convex, or in this case, a converging lens. And you can see here, if I put the object on this side, the image is going to be over here. Now, where would I be if I'm the observer? Well, I'd be right on this side looking through the lens that direction, right? Through the lens. And the other side of the lens would be the object I'm trying to look at, because I want to look through the lens at that object. It's kind of like a magnifying glass. I want to see what happens. Okay. So the object's on that side. And then in this situation here, I would see because the image shows up on the same side as me versus where the lens is. So there's a lens here, the image is here. Because it's on the same side as the observer, this would be a real image, very similar nomenclature as the mirrors. So I can move this around. You can see what's happening here. These beams are there because they're refracting. They hit the mirror or the lenser, and then they bend twice. So you want to show the one bend here because we're assuming these lenses to be ideally thin. So you don't have to worry about the two bends, but the two bends would cause this line that's going straight across to bend towards the focal point and then continue on through. If I were to go through the vertex here, like the center of this lens, that beam would bend twice, but it would bend twice in such a way that it would almost seem like it came out exactly the same direction that it was coming in. Right? So a straight line there. And if it goes through the focal point, we're going to see the focal point on both sides are the same. If it goes through the focal point, it's going to bend twice again, and then come out parallel on the other side. You can see that they converge in this one spot. So I would see an image here, kind of like a floating image, it's an optical illusion-ish. It's hard to see that kind of image with a one-dimensional camera. You'd have to actually see it in person. It's something that kind of floats there in front of you. You can almost think you can grab it, but you can't really. And I can move this around. You can see what's happening to the image. You can also see that it's inverted. It's upside down, right? It looks diminished in size, yeah. Because if I put it here, let's put it here, because that's too tall. It's not quite too tall on this side, so it's diminished. Oh, right here, you can see the height of the image is smaller than the height of the object. All right, I can move it around. You can see that at 2 times here. No, the two times that have the same height, very similar to reason having it on the center point on a mirror would give you the same calculations. And you go a little bit further, you can see that it's getting a little bit more, it's getting larger over here now. So it's enlarged. Okay, still real, still inverted. You get on the focal point, same reasoning the mirror had no images because the lines are parallel to each other now. As you go the other way, you could see that if I'm inside the focal point, I'll put it here. The rules still kind of apply. If I'm going straight across, it's going to bend towards the focal point. If it's coming from the focal point, it goes parallel through the middle, straight on through. But if I trace the lines back now, they're coming back here. So now I have a virtual image behind the lens. And now this is the typical case of a magnifying glass, right? You put it really close to the object, it makes it much larger, and it creates a virtual enlarged image. So you don't see the object, you only see the image, right? The object is not there, you never see the object. So even in this situation, I don't see this object behind the lens, I only see the image that's on this side. Okay, so let's move that in more, and you can kind of see what's happening here. Now it's upright or erect, it's enlarged, it's a bit larger on both sides, it's also virtual. Okay, so that's what a converging mirror looks like, or in this case, convex lens. But I like to call that a converging lens, converging lens. Now I'm going to change this to the other side, and we'll do a diverging one. So this is a diverging one here. It's a bit trickier to see what's happening here, but I guess you can see that, again, I'm on this side. Here I am, right here. I'm looking through that lens that's over there. The object is on the other side of that. All right. So what I see here is I see this little diminished virtual image right here, even though the object's here. Now the lines are there. How they work is that if I go straight through, just like the previous one, it goes straight on through. If I go towards the focal point on the other side, it levels out because it bends twice. And if I go straight across, it bends outwards as if it's coming from the focal point on this side over here. And then you notice that they both converge on this side. And if I go through this, you notice that I always have, no matter where I am, always have a virtual image, very similar to a convex mirror, where you always have a virtual image, because that's technically a diverging mirror. That's what it looks like. So this applet, if you want to look at this applet in a little bit more detail, I will put the link in the Google Classroom. Okay? So let's go back to our notes here. So I'm not going to really draw, I'm not going to draw these diagrams. I'll never expect you to draw the diagrams, but I'll expect you to do the math and then tell me the type of images, the magnification, the attitude, is it erect or is it inverted? The magnification, is it enlarged or diminished? Where's the position? Is it real? That's the type. Is it virtual? Now, the fun thing about this, it is all exactly the same as the mirrors. All the sign conventions the same and everything else. Just the wording's a little bit different here. So a converging lens is the same as a concave mirror. They both have positive focal lengths. A diverging lens is the same as convex mirrors. They have negative focal lengths. So that's very, very important for doing. It's just this last line that's pretty much the difference between the two, right? Diverging lenses have negative focal lengths and converging lenses have positive focal lengths. It's a very bad color for highlighting. So let's change the highlight color. Yeah. So those are important. Those are the differences between these two. Everything else is the same. A real image is positive. A virtual image has a negative distance. If it's inverted, the height is negative. If the magnification is negative, it's also inverted. If it's larger than 1, it's enlarged. If it's between 0 and 1, it's diminished. So everything's the same as the mirror calculations. The formula is also exactly the same. So you're going to be using the exact same equation as the mirror one, right? It's 1 over f is equal to 1 over di plus 1 over do, and the magnification formula. So all that is exactly the same. So what I'm going to do is I'm just going to stop here. Actually, before I stop here, I'm just going to write down the formula that we're going to be using for all this. So 1 over f is equal to 1 over dO plus 1 over di. And the magnification formula, hi over ho is equal to negative di over dO. There you go. Okay, so those two formulas are exactly the same. We're going to be using those exact same equations to do these kind of things. What I want you to do is try out these next 3 questions. The only thing weird about this last one here, about the projector, is that the image, because you are on the same side as the image itself, that is considered a real image. Right? On the other side of the lens in the projector, that's where the LCD part's happening. That's where the object is. It goes through the lens and it's on the same side as you. So in this third question here, this focused image is a real image. Okay, so this 5 meters away, that's the real distance. That's a positive 5. Okay. So I want you to try out these 3 questions. I'll see you in the next video. Bye.